Welcome back to the 2019 RASC-AL Forum. We're continuing now in Theme 3, Gateway-Based Human Lunar Surface Access, and our next presentation is from Virginia Tech.
Good morning, thank you for having us. We are Project Ladon, an engineering design team consisting of 12 aerospace engineers from Virginia Tech. We have developed a design for a reusable, gateway-based human lunar surface access vehicle that will be delivered by the year 2028. This is our organizational chart. Our faculty advisor is Dr. Kevin Shimpaw. The first thing we did is we split ourselves into 6 sub-teams, each responsible for a key technical area associated with the design of our proposed vehicle. And now Colin is going to go over the process we went through for problem definition.
So the goal of this project was to provide a vehicle, a reusable vehicle, that will provide gateway-based access to and from the lunar surface and support the Gateway crew in their missions over the Gateway's 15-year lifetime. Now, the motivation for this design stems from NASA's current goals for human space exploration. These are to establish a permanent, sustainable presence on the lunar surface, utilize that presence to develop and test human spaceflight technology, and then leverage those technologies in applying forward to Mars missions. Some of the needs, alterables, and constraints we were able to identify with this project include a reusable means of accessing the lunar surface from the Gateway, and also an initial architecture proposal that is not dead-ended. We have also identified some of the alterable components we were allowed to perform trades on, namely some of our propulsive elements, including the distribution, number, location, and staging of these elements, and also the types of propellant and the propulsion systems that we used. Some of the constraints include the delivery of the crew to the Gateway utilizing NASA's SLS and Orion. Additionally, our interfacing with the Gateway, and also our frequency of operation at a minimum of once per year. And now, some of the requirements we were able to derive from the initial customer requirements given. We performed the requirements flow down to try to come up with some technical specifics regarding some of our subsystems as far as performance are concerned that really guided our design process. So shown here is just an example branch of the requirements flow down that we performed during our analysis, and these really drove our design. And now Don's going to talk about the ConOps.
Based on our RFP, we were able to develop the following ConOps. Initially, NASA will fly the crew from Earth to the Gateway using the Orion capsule, and from there, our mission shall begin. From there, we will use our transportation stage to transport the crew from the Gateway to a low lunar orbit, and then our lander will transport the crew the rest of the way to the surface. They will then proceed to do their 2 to 6 day mission, depending upon the mission mode, and then return back to the low lunar orbit, where they will rendezvous with the transportation stage. Transportation stage will then return to the Gateway, and the crew will be transported back to Earth via the Orion capsule. This will happen during the 1-month manned Gateway period that will happen each year during the entire 15-year Gateway lifespan. In between these 1-month periods, we will have resupply runs and fuel runs so that our system is completely effective and it will not have any issues when the crew arrives at the Gateway. From our information, we were able to produce a value system design. We found that there were 3 main aspects that we wanted to focus on: the performance, the cost, and the risk of the system. Within our performance, there were 2 main effectivenesses that we wanted to evaluate. That was mission effectiveness and system effectiveness. We evaluated mission effectiveness based upon our payload capacity, since we wanted to maximize that to allow for more versatility, and the versatility could be affected by where exactly we could land on the moon and how long our mission could be. For the system effectiveness, we wanted to minimize the technical requirements, such as the mass and the power required for our entire system, where we wanted to increase the operable conditions in which our system could launch, and the specific factors that would affect when we can actually launch our system and when we can do our missions. Cost and risk will be evaluated further on in the presentation. Evan will now go over the human factors that we considered for our mission.
Thanks, Tom. So, the Human Integration and Design Handbook, NASA's Human HIDH, and NASA Standard 3000-3001 were used heavily in our design concept and was used to create, requirements for each sub-team that was on our team. And some of our main considerations were nutrition, acceleration loading, waste management, radiation, atmosphere. Some of our main requirements that we had as a human sub-team was to sustain crewed lunar access to the surface. We also wanted to provide a 7-day contingency period based on HIDH, and So for acceleration loading, we from HIDH, we found a time versus acceleration factor chart, and using this chart, we came up with a 4G maximum trajectory for no more than 15 minutes, and this was to ensure that none of the effects happened to our crew, shown in the chart. So here you can see emission duration versus total pressurized volume, and this is directly proportional to our crew size, the mission duration, and how much habitable space we need in our lander. So with the 4 crew members in mind for this competition, we came up with 39.2 meter cubed as our minimum, and our final habitable space came out to be 69.7 meters cubed. Here you can see our atmospheric composition and the resources that are included in our human mass budget.
We established a radiation dosage limit using this chart here from the HIDH. Initially, our dosage limit was 200 milligrays, but as we did more research on long-term negative radiation effects on the Apollo astronauts, we looked at the radiation seen on each of the Apollo missions and came up with a new do not exceed limit of 25 milligrays of radiation. We also looked at carbon scrubbing, focusing on 2 major methods, one being the more traditional lithium hydroxide carbon scrubber, the other being a 2-bed zeolite carbon scrubber. The lithium hydroxide carbon scrubber has a lighter initial mass, but is non-reusable. So over the 15-year duration of our mission, the 2-bed zeolite carbon scrubber outperformed the lithium hydroxide because of its reusability. As for waste, we decided that a majority of the human waste would be left in bags on the moon, as they did in the Apollo missions, to decrease mass when the lander takes off, as well as mitigating impact on the gateway, and that any waste produced in transit back to the gateway would be disposed of into space. As for the interior of our design, we have 3 floors connected through the center through a ladder. The top floor will be for monitor systems, command and control, and will be where the astronauts reside during takeoff and landing. The middle floor will be where the astronauts spend most of their time, and will have areas for their beds, leisure, meal prep, personal hygiene, and donning and doffing clothing. The bottom floor will be where we actually have our lunar surface access. So this floor, it has a height of 2.8 meters as opposed to the other 2 floors with a height of only 2.2. The reason this bottom floor is larger is because our astronauts will need to enter through our hatch wearing their EVA suits. This can also serve as a radiation shelter in the event of a solar proton event or any other large radiation event. And now here's Patrick to talk about orbits and trajectories.
Thank you. So the trajectories and orbit subteam focused on defining the orbital environment, particularly the trajectories and maneuvers needed to accomplish the mission, along with extracting from that the necessary delta V budgets and axis data between objects of interest. Our requirements stem mainly from the lander level 2 requirement that the lander shall be capable of performing any necessary orbital maneuvers, and this can then be broken down into sub-requirements focusing on what kind of orbits it can transfer between, where on the moon it can land, how much extra delta V it needs for contingency, and how long it has to perform these transfers. One of the main orbits of interest is the NRHO, or the Near Rectilinear Halo orbit, which is the orbit the Gateway is expected to be operating on. And it's a Earth-Moon L2 orbit and a southern orbit as well, so the landing site near the South Pole will have substantial coverage to most of the Gateway's orbit as well during the mission. Upon analyzing our trajectory, we found that we have about 5,000 meters per second of delta V in total. First, it begins with a small burn at the NRHO, and then the spacecraft leaves the Gateway, moves on this blue trajectory towards LLO, or low lunar orbit, about 100 kilometers off the lunar surface, at which point it then performs a descent maneuver to land on the lunar surface. After performing the mission and waiting for the Gateway to reach the right position for rendezvous, it will reascend back to LLO, and then follow this trajectory back to the NRHO where it redocks with the Gateway. And as you can see, the descent and ascent portions are by far the most expensive parts of the mission, which is why we looked into some different staging options. We examined 2 possibilities, a single stage and a 2-stage design, where the 2-stage design with the lander and the orbiter would have the lander performing only ascent and descent and the orbiter performing all other burns. And we found after the analysis that the 2-stage, although far more complex in design, has a lot of mass savings, and thus we determined that the 20 metric tons it would save is worthwhile to consider, so we went with that as our design option. And now to talk about how to get these delta V's, here's propulsion.
Thanks, Patrick. So propulsion was initially. So propulsion was responsible for selecting the appropriate propellant, selecting an appropriate engine for the orbiter and the lander, as well as conducting a staging analysis to find the appropriate propellant masses, as well as sizing the tanks. So our first two requirements stem from the human subteam with the acceleration loading, and as well as the delta V requirements given to us by ATO. And the third and final requirement was the contingency boil-off, which we accounted for in all of our propellant masses. Here's Brennan with the propellant selection.
Thanks. So we conducted a propellant trade study comparing 3 different propellants to consider in our design. And we analyzed estimated mass and volume values using an approximate total delta V for each mission. And these mass and volume estimates can be seen in the table above and bar graph below. And taking these numbers into account, we concluded that liquid oxygen and liquid methane would be our propellant of choice. As it's clean burning, it's not as toxic or corrosive as other hypergolic propellants and experiences less boil-off than liquid hydrogen, and also has possible future ISRU on the Martian surface.
So the next thing that we had to look at was possible engine configurations. So the 2 engine configurations that we conducted a trade study on were a single engine configuration that was similar to the Apollo missions and a more complicated engine ring truss structure. And what our trade study concluded was that although the engine ring was more complicated, it offered greater redundancy and versatility and maneuverability when coming down to the lunar surface. So that's what we decided to go with.
Our engine ring design offers an increased level of redundancy and propulsive versatility, specifically the ability to remain fully functional in the event of 1 or 2 coincidental engine failures. And this is achievable due to the HD4 engine's throttling capabilities to be able to maintain a center of thrust in line with the central axis of the lander. And these diagrams show throttling maneuvers which can balance the lander in the event of whether it be different combinations of engine out scenarios, whether it be single or double engine failures.
So here you can see our final lander configuration with the engine shown and the propellant mass breakdown accounting for a 5% boil-off. The chosen engine was the Project Morpheus HD4, and its specifications are outlined at the table in the bottom of the slide. Here we have the orbiter mass breakdown, again accounting for a boil-off contingency of 5%. Both of our engine masses were calculated using historical data, so that's how we got the 136 kilograms and the 600 kilograms respectively. And again, the engine for the orbiter was the AVO M10, another LOX methane engine whose specifications are outlined in the table at the bottom.
So the lander will have 7 liquid oxygen and 8 liquid methane tanks, all located on the truss structure surrounding the lander. And because the HD4 engines are pressure fed, they will require helium to pressurize the tanks, and these tanks will be located inside the vehicle. And for the orbiter, it will have 4 of these COPVs to house the fuel and oxidizer necessary for the AVO M10 engine. And because the M10 is pump fed, it will not require the pressure that the lander does. And these values are, the masses and dimensions are displayed above for the lander and below for the orbiter. And in summary, using these delta V requirements, propellant characteristics, and geo-loading limits, our analysis led to the orbiter having 1 singular AVO M10 engine and 4 COPVs to house the propellant. And additionally, 8 Project Morpheus HD4 engines will be located on the engine ring surrounding the lander with a total of 15 propellant tanks. And on the right is a table displaying the total mass and power estimates for the propulsive elements of our design. And now I'll pass it off to Newton and Danielle to talk about structures.
Thank you, Brennan. So the main goal of the structure subteam included these 4 design considerations, such as vehicle structure design, the analysis of the design, the radiation protection of our lander, and also the docking mechanisms that we'll be using. So our main requirement for our lander flowed down from the human factors subteam, and it was that the lander shall be able to accommodate and protect the crew and cargo during all the mission phases. From this higher level requirement, we were able to get sub-level requirements related to the habitable volume, the withstanding the vibrational loads, remaining stable for the entire mission, and also having a high factor of safety. For our orbiter, we had a requirement for docking to the lander, and it must be compliant with the IDSS.
So here are our final designs for the lander and the orbiter. The lander has a total available volume of 69.7 meters cubed and weighs approximately 6,800 kilograms. The orbiter is not going to be housing any astronauts, so can employ a simpler truss design to hold its components, and weighs approximately 350 kilograms. So for our lander, we designed a truss design to hold the propellant tanks for propulsion, and we also designed a truss design for the orbiter. And we put these designs and the legs through a system called FEMAP in order to determine the maximum stresses experienced throughout the mission. All the maximum stresses are well below its yield stress for all the materials used and has minimal deformation, so our mission will be safe.
One of the most important aspects of our mission was that we should have adequate radiation protection to protect the crew and cargo during the entire span of the mission. So based on this graphic to the bottom left, it is seen that the galactic cosmic radiation is the main source of radiation will be encountered, and roughly 10 grams per centimeter squared will adequately protect our crew and cargo. We looked at two different materials, aluminum and polyethylene, at shielding our lander, and varied the thickness of the polyethylene from 1.5 centimeters to 3 centimeters to see how much protection would increase. So as we expected, protection increased as we increased the thickness, and the exposure limit went down as well. So in order to be compliant with the requirements, we had to be under 25 milligrays of radiation during our entire mission. We ended up going with the condition in the green box because it both saved mass for our design and also kept us at 23.5 milligrays during our mission, which was less than the requirement.
So we use two different docking mechanisms for our lander. We use the international docking adapter for the lander to the gateway, and then we use the NASA docking system between the lander and the orbiter.
So for our final subsystem design of the structure subteam, in order to meet our structural material and analysis requirements, we ended up choosing an outer hull made of an aluminum lithium material that was 0.5 centimeters thick. The truss structure that we had surrounding the exterior of the lander, holding the engines and the fuel tanks, had minimal deformation, and it also had a factor of safety that was much greater than the required 1.65. For our docking requirements, we ended up choosing the NASA docking system and the international docking adapter. And for our radiation exposure requirements, we went with the material polyethylene because of its high hydrogen content, and also aluminum because of its historic use in shielding in space applications and its success in those applications as well. Our final structure subsystem masses are also shown in the table to the right. And now here's Colin with attitude and orbital control systems.
Thanks, Nate. So the Attitude and Orbital Control System subteam is responsible for attitude determination and control, as well as orbit determination and control. Now, due to the critical function of this subteam in most of our spacecraft's operations, our main requirements were stemming from our communication systems as well as our docking systems, but we really opted to choose components that would meet our requirements while maximizing reusability and reliability so that we could optimally perform these functions throughout the lander's 15-year lifetime. So our main method of control will be RCS thrusters. These thrusters are aerojet thrusters, providing 275 newtons of thrust per thruster. They're going to be arranged in 2 blocks. The lander will have 4 blocks of 7 thrusters each. The orbiter will have 2 blocks of 5 thrusters each, so that they each have full 3-axis control for fine and coarse attitude and positional control maneuvers. Some of the other components that we're going to be using are star trackers with redundancies on both the lander and the orbiter for our attitude determination. We're going to be using IMUs for orbit and positional determination, as well as NASA's Project Morpheus LHAT LiDAR sensor suite, which will provide enhanced safety and precision during our landing maneuvers. For attitude positional control, as I mentioned previously, we're going to be using our Aerojet Rocketdyne MR107S thrusters arranged into RCS block configurations, and the masses and powers for each of those systems on the lander and the orbiter are shown in the table to the right. And now we're going to go to communications, command, and data handling.
So CC&DH was responsible for designing two different types of data transmission, a high data rate and a low data rate, command and control for the vehicle, as well as data storage. For communications, we started by identifying the specific data rates that we needed for the different nodes that we were in. We picked frequencies, modulation techniques, different aspects of our design to be compatible with the proposed architecture of the gateway. And we also made sure that we met performance criteria such as minimum or maximum bit error rates and link margins. For command and data handling, we started by identifying key requirements involving reliability and desired functionality of the system. So for communications, we decided to go with an optical system for our primary surface communication. We went with this because we had a very high data rate, and this system offered mass and power savings compared to a traditional RF system. We are also using a redundant Ka band system based on our link budget analysis. And the lander and orbiter will have both an omnidirectional S-band system for transmitting critical data in transit, and a UHF system for communicating with surface assets and during docking procedures. So the total mass for the entire vehicle for the subsystem was just under 300 kilograms. For command and data handling, for command and control of the lander, we decided to go with 4 computers in an architecture similar to Orion. These computers have a high degree of reliability, and by 2028, they will also have a lot of flight heritage. For the command and control of the orbiter, we went with less powerful computers because less data-intensive tasks are required. For data handling and storage, we went with the system based off of NASA's disruption-tolerant networking system. And we also included a 5th redundant command and control computer for the lander with a different set of software in case there's a bug in the primary software. So the total mass of this subsystem for the entire vehicle was just under 400 kilograms. And now we're going to go to Teddy and Chris for the EPS.
Thanks, Bud. We needed to consider power generation and energy storage requirements on both the orbiter and the lander for our electrical power system. And our requirements are based on historical trends, and they provide us a baseline limit for what we expect our power demands to be. To paint a clearer picture of what subsystems and components would need all this power, we came up with a power budget for both the lander and the orbiter, and after adding a 25% contingency, we came out at 11.9 kilowatts for our lander and 1.19 kilowatts for our orbiter. This came well below our limits that we set in the requirements. To show when this power would be used, we came up with a sand plot showing the different phases of a mission. For example, this one shows a 7-day mission with a 7-day contingency, and this allows us to see what energy, how much fuel we require, and what systems are on during different phases of the mission. So we decided to go with fuel cells because we had a relatively high power demand, and of the 3 fuel cells that we looked at, we decided to go with the proton exchange membrane fuel cells because of its balance of technology readiness level, and it also has a high gravimetric power density. These fuel cells also produce water, which is a valuable resource for our thermal cooling and our crew drinking water. While we strongly considered the solid oxide fuel cells because they use the same propellants as our propulsion system, we eventually decided that the technology readiness level was simply not at the technological fidelity we need to recommend the solid oxide at this point.
For the orbiter power system, we decided to go with solar cells because they're the most efficient, and it's always going to be in the sunlight. And for the mission duration that the orbiter is going to be in use. And for the solar cells, we decided to use triple junction solar cells because of its efficiency compared to other types of solar cells. And we have 2.5 kilowatts of available power for the required 1.19 kilowatts of required power, with contingency to power the gateway, power the lander at the gateway. Alright, and for the energy storage, we decided to go with lithium-ion batteries. And we researched 3 different types of batteries: lithium-ion, nickel-cad, and nickel-hydrogen. We decided to go with lithium-ion because it had a higher energy density and a really low self-discharge.
Right, to summarize, we'll be going with modified Ballard proton exchange membrane fuel cells for our orbiter power generation, the Spectralab solar arrays for our orbiter power generation, and 14 stacked lithium-ion batteries for the energy storage required on the orbiter. For our thermal control system, these were our main design considerations. The requirements were based on the different operating temperatures and the environmental conditions that our spacecraft would be under. The active system was present on our lander, and this is composed of a 2-loop architecture based on the Alters design, which is designed to acquire, transfer, and reject heat through the sublimators and radiators that we place throughout the spacecraft.
And we will be having a passive system on both the lander and the orbiter. And here on the left is going to be the layering of the MLI that we will be using. And we'll also have a reflective coating on the outside to prevent heat and stuff like that.
All right, here's Dominic with the technical budgets.
Thank you, Tate. So, as you can see here, based upon our subsystem designs, we were able to come up with the following mass budget for our lander. We were able to include allowable growth rates based upon AIAA standards throughout the entire duration of the development period. As you can see on the far side, the propellant is actually the largest contributor to the entire total mass, with the entire total mass being between 32.5 and 38.7 metric tons, and the dry mass being between 9.5 and 11.2 metric tons. Similarly, we were able to create the following distribution for the orbiter itself, with the propellant still being the largest factor. The total mass was between 14.6 and 17.1 metric tons, and the dry mass was between 1.57 and 1.8 metric tons, meaning that our initial launch would have to be able to support a 13 metric ton launch for the dry mass. We also had to do yearly resupply missions because there are a lot of expendable resources that we have to use, such as water, atmosphere, and propellant. We found that those values are going to be between 35.2 metric tons and 41.4 metric tons per year. When considering how to launch this, we considered several different launch vehicles, including the SLS. Initially, the SLS seemed to be a large factor in our design, but upon recent developments, we have determined that the SLS is a bit inferior due to the time constraints of the design. We did determine that the initial launch would be best done by the New Glenn due to the fact that it does reach our initial launch criteria for the dry mass, and the Falcon Heavy can be used to launch our resupply missions. These are both fairly cheap, and they do allow for an increase in mass. Since for the Falcon Heavy, we will do 2 launches per year, and with those 2 launches, there will be excess area inside of the launches so that we can do ride sharing to the gateway. From a timeline perspective, we have it so that during the entire year period, starting from the mission duration and going plus and minus 6 months from the start of the mission, we will do 3 vehicle analysis checks from the ground station. This is to determine if there are any issues with the system. We can send up replacement parts during the resupply mission. The resupply mission will happen as close as possible to the actual start of the mission period. That way, as little boil off can be seen. Prior to the crew doing the mission and prior to the crew finishing after the crew finishes the mission, they will do a full vehicle check as well as a second safety precaution. Based on all of our information, we found that there's going to be a total commercial cost of about $16.1 billion over the entire duration, assuming that we would start today with further design and development and ending at the end of the gateway period. Now Colin's going to go over the risk management system.
Thanks, Dom. So an important aspect of the systems engineering design process is the identification and quantification of risk. So shown here are a few of the risks that we have identified with this project. Now a project of this scope has a lot more risks than shown here, but we opted to focus on those that we felt we were most able to affect throughout this conceptual design phase. So with these risks, we were able to plot them on a 5x5 risk matrix to try to get a handle on the relative magnitude of each risk. So from this point, looking at the probability and severity of each risk, it looks like our most probable risk is the schedule overrun, which is because a project of this scope might have problems with slipping schedules, which would jeopardize our ability to deliver our vehicle by 2028 and could reduce the number of total missions we could perform over the Gateway's 15-year lifetime. So with each of these risks, we were able to further analyze them and separate them into 3 categories, namely mitigate risks, transfer risks, and accept risks. Mitigate risks are those we can directly affect throughout our design, which include things like component failures by including redundant components. Transfer risks are those we are transferring responsibility for to the entity responsible for providing us with that component, such as choosing a launch vehicle from a provider with a reliable launch history. And then accept risks are those that we have no direct effect towards during our design process, but we can still prepare for, such as medical emergencies occurring with the crew. So finally, in conclusion, to summarize, we have proposed a design with a lot of applicability towards Mars missions through our use of potential ISRU utilizing propellants like LOX methane. We also utilize a lot of COTS components to simplify the acquisition of components as well as reduce cost. We have mass savings compared to an all-up design through our choice of using a lander and an orbiter. And additionally, our engine truss string through the use of the 8 Project Morpheus HD4 engines allows us to mitigate engine out risks by providing redundancies there. Our total mass is expected to be 45.5 metric tons, and we expect to have a total cost of $61 billion over the course of the 15-year lifetime. We believe that this is an effective design in response to the RASC-AL 2019 Theme 3 competition. We would like to thank our advisor, Dr. Kevin Shimpa, for his mentorship. This has been a very educational experience for all of us, and thank you very much for your attention. Are there any questions?
I guess I'll start over here. Oh, that's great, Kevin. Kevin on the moon. Great job. Glad to see that you put contingency on your mass and other subsystems. That was pretty good. How did you determine the probability in your risk or your risk entry point for many of your items? How did you do that? How did you get that entry level that you went in with?
So our main factor there was trying to essentially look at historical risk analyses. We did some studies on historical risk analyses, trying to see what the probabilities they went with were and trying to apply those to our designs as well. And also we tried to take into account some of the design concepts that we went with, including system redundancies, to try to give a ballpark for some of the probabilities as well as the severities of consequence that we would experience should those risks occur.
Okay, so Lassen, how did you determine your New Glenn and Falcon 9 Heavy TLI performance?
So the New Glenn's performance in terms of how far it could go and its ability, from the ULA website, they specifically say the payload restrictions from it in terms of both the size of the payload fairing itself as well as the mass requirements. For the Falcon Heavy as well, they also have similar numbers.
Yes, but I know if I go on the Falcon 9 or SpaceX website, they don't quote TLI performance, and that's what I'm saying. You had to come up with a way to do that as well as the other.
So for some of those, specifically the Falcon 9, there was some analysis we'd found doing some research online where people had sort of speculated what they expected the TLI performance to be based on historical performances as well as performing extrapolations of those performances. So that's what we based on. Those numbers are not final and those could change, but based on our best guess extrapolations, that's what we used for our TLI performances for both the Falcon 9 and the New Glenn.
So great presentation. I liked the way you linked your solution to your requirements. You know, this is what we need, this is what we did. So that was great. Can you go back and talk about your docking systems? You used 2 of them. What are the differences in them, and why did you use 2 versus 1?
So we used 2 because to reduce mass, we used a soft capture system between the orbiter and the lander because the astronauts do not need to pass through and it's not pressurized or anything, while the astronauts will need to travel from the lander to the gateway, so that's why we chose the international docking adapter for that. So using 2 separate ones ended up reducing the mass for the overall system.
So aren't they really the same except for the tunnel between them for the crew?
Yes.
Okay, thanks.
Yeah, hey, good morning, nice job. So the first question is, look like on your initial propulsion trade, you kind of stepped on the scale a little bit for the LOX methane. You had a 380 second ISP, which is probably a little sporty, but only gave the LOX hydrogen about 435. So I wasn't sure, I don't know if it really changed your assessment or what you decided to go with, but did you have any comments on that? You know, with cycle differences you were assuming, or why?
Yeah, so that trade was pretty early on in our analysis. So what we did, we basically took kind of like average values for each
propellant in terms of ISP. So I guess because the HG4 only has an ISP of around 321, which is definitely not near 380. But we use averages for that trace study, so of course it's going to vary a little bit in terms of calculating the mass, like propellant mass.
Okay. And my second question was on your finite element modeling. Can you talk about some of your load cases? Did you look at any off-nominal cases or engine out with the non-symmetric distributions?
Sorry, could you repeat the question?
Yes, for your FEA analysis here, did you look at any off-nominal load cases with an engine out, non-symmetric distributions, or were they kind of all ideal or nominal landing conditions or with engine operation and uniform loads?
Yeah, these were all nominal cases because they were modeled as a simple static analysis using beam elements. So we didn't look at any off-nominal with any additional moments applied or anything like that. Just having the landing load or the thrust load applied at the specified points.
Good morning. Good job. Have one question, and that is you showed the engine throttle percentages for 2-engine out configuration. How many engines can you lose before you become not able to fly?
2 would be the max, because if we have coincidental 2 engine failures, even the worst case scenario, which is the middle left diagram, it produces 63 kilonewtons, which cuts our total cable thrust in over half, but still provides a thrust-to-weight ratio in lunar gravity of 1.2 during descent. So during ascent, the ascent phase, it will be around 2, with still having 6 engines working.
Good morning, nice job. I really like the systems engineering flow, how you restated the requirements at that particular place in the flow down and then showed the implications of responding to those requirements. Question for you. Your cryo tanks, both your LOX and your methane are composite. How did you get comfortable with a composite cryogen tank in both cases?
So I think our main reason for using composite tanks was the mass savings when compared to aluminum lithium tanks. And as with the cryo capability, I think we need to look more into, I guess, the pressurization and depressurization, and look at the stress that would exhibit on these tanks to fully justify the use of the COPPs rather than just saying that they save mass.
Okay, thanks.
Good morning, and I appreciate all of the fault tolerance and margin that you put into your system as representing the crew in a lot of designs for upcoming programs. That's critical. Don't let any program manager take that away from you. That's where they go first when there's cost and schedule hits. But my question is, I think your orbiter is using a single engine and you have a lander with multiple engines, and your rationale for the multiple engines on the lander was because you had a lot more redundancy and capability. But then for the orbiter, you only had a single engine, so you didn't apply the same philosophy there. So what was your rationale?
So the rationale for that was since the orbiter will primarily be in orbit waiting for rendezvous with the lander, it doesn't need a high degree of redundancy, and that the engine that we selected had a high number of available tested restarts. So in the case of a failure, I believe the AVO said that it was tested up to 50 restarts.
But if you had a failure that was non-recoverable, you had no options unless, is there a possibility of using any of the lander engines for that kind of
Yeah, no, we can, if the lander, yeah, we definitely have fuel in the tanks in the lander when coming back up. So we have with using the available contingent propellant mass, we'd definitely be able to get out of there in case of emergency.
Thanks.
I have a few more questions during the poster session, but what was the thinking for the window placement as far as like human factors point of view?
So there's actually a requirement in the Human Integration Design Handbook that specifies at least 2 windows. We decided to put 3 windows plus 1 on the hatch, which is another requirement, the one for the hatch. So we have 2 windows in the top portion. You can see one there, and that's just because that's where the astronauts are going to reside during takeoff and landing and need to see their surroundings. The other window on the middle floor is just in the leisure section and can also be for photos, optics, experiments, that sort of thing. And then the hatch window is a mandatory requirement that was specified in the HIDH.
All right, thank you, Virginia Tech.